This meeting is being.
Hi, everybody, and welcome to today. Actually, it's test day, so we're gonna probably leave at 2 o'clock, which is probably not too far from what we have been doing in the past. The exam is going to be available at 2:30 p.m. today, just when the lab time starts. So I will be watching basically for any messages if there is any problems with the exam, so that if you have an issue, please send me a message right away. I will not be having a Zoom session available at that time because the exam, I think like 5 hours or something like that. The window for it, you guys have only a shorter window than that. So you have, I think you're going to spend about 2.5 hours basically of doing the exam, and also an additional hour to figure out basically on how to upload stuff and everything else. That is the time once you start the exam. After that, it's going to close on you. So please take that exam and do it as soon as possible, and to avoid any kind of mishaps down the road, and then you figure out that there is an issue with it. Exam 3 is chapters 27, 28, 29. Those are the 3 chapters covered in this exam. Today's topic is actually chapter 30, which is the new basically group of chapters. 30 and 31 and 32 are exam 4, which is going to be immediately after Thanksgiving. This week we will do part of chapter 30. Monday we will finish chapter 30 and start chapter 31. We will finish chapter 31 by Wednesday. Then we take the break for Thanksgiving. Then when we come back from Thanksgiving, we should be able to finish chapter 32. And we will have the exam immediately after. And after the exam 4, we will have the final. So basically, this is how, in terms of testing, where we are. And that's the content. We still have few labs to go through. Next week, we will have the AC lab. And probably we'll also add to it the Rlc circuit too. So we'll have the oscillator there, because by then we will have covered the topic related to it. So this is basically everything that I have in mind in terms of announcements. Hopefully you guys will meet later on for the exam. And I mean, you guys not meet, I guess you guys have to be on your own and take the exam. And of course, this Wednesday we don't have a class, it's a holiday. Okay, so let's get going with the topic.
Excuse me, Professor.
Yes.
The exam 3 is being given out through Canvas, correct?
Yeah, through Canvas. You have to log into Canvas. You should see a link right now if logged into Canvas. Of course, it will tell you it will not be available until 2:30 p.m. today.
Well, it also says it's not available until November 10th.
Are you serious?
Yes.
That's bad. Okay, maybe I messed up on the date. I'm glad that somebody was. Otherwise, hold on. Let me check it. Modules. There are so many things I was doing, so maybe I clicked on the wrong day.
It's okay. There's just a little confusion.
Is it November 10th when it's... Oh man, let me go back. I see November 10th, but that I thought... Okay, hold on. Let me edit it. Because once you put it through that thing there, exam 3, edit. Takes me right through taking it. I don't want that. Let me go to the settings in here. No. Oh, I know how to get to it a different fashion. Because once I click on it, it takes me just as if I'm going to take it or edit it from there or something like that. So let me go to assignments in here and find it from here. Exam 3. Edit. More options. I think you're right. I'm glad that somebody was setting. So it's going to be today, 2:30 p.m. Thank you very much for pointing that out. And which exam I was then fixing earlier? Oh man, oh man, hopefully I didn't do it because I was doing another class also for them. So I'll have to go fix that class. Okay, so 2:30 p.m. and this is available for 2:30 plus 6, that's 8:30 p.m. So it's going to be available until 8:30 p.m. So you have about 6 hours window just in case if you were working. And 8:30 p.m. Very good. So let me make sure I have it. November 9th, November 9th, November 9th. Sometimes you get too focused on the day and the time. Yeah, so what's wrong with that? Unlock date cannot be after due date. Oh, available, you're right. Okay. How's that now? Save. Okay, let me make sure that the savings worked.
It looks like it did.
It changed on you? Okay,
Yeah, it says November 9th at 2:30 p.m.
Okay, let me make sure the ending though is the same time that I had in mind, because I want to make sure that I did not. Sometimes you're focused on the time and you forget the date, and that's probably the date is more important than the time. Edit it. More options. The grid looks correct, and the attempts look correct, and it doesn't matter really the number of attempts, because this is not like the previous. It's slightly different in the format than the previous exam. So from 2:30 to 8:30, you have 6 hours window. Okay, but once you start it, it's going to give you about. That's fine. Okay. So save. Okay, so we're good.
Professor, I have one question.
Yes.
So the exam 3 won't be how exam 2 was, where we had to put our answer in. So do we need to be correct with our sig figs?
Please at least allow 2 decimal points. I really don't care much about the sig figs, except the 2 sig figs, 2 decimal points. Okay. Try to keep at least 2 decimal points to make sure that you're accurate in terms of the numbers. This is all file uploads now. There is no fill in the stuff. It's similar to some extent to some of the versions before. Okay.
Okay.
So
thank you.
No problem. So well, let's start the discussion for chapter 30, because that's also something that is, unless you guys have another question. I'm glad that somebody was caught this issue here. Otherwise, we will have a problem. And that means that another class that I have to really fix quickly had the exam switched with you guys, because I have another exam today also for another class that is supposed to, so maybe they will have their exam in the wrong time. Okay. See what the elections does to you? You're paying too close attention to other things.
The madness.
It's really crazy. Anyway, it's still not over yet, according to. Okay, so this is the topic of the day today. Let me go back into the content. So we're going to talk today about. Why is it not showing? I need to see this. Okay. And my Zoom is not working correctly now, which is fine. Okay, so basically what we have in this case is we have the fact that the law of Faraday basically state the following: that if the magnetic field changes, okay, that will induce a current, basically induce an EMF, not a current necessarily. Okay, an EMF that could potentially induce a current if, of course, I close the loop. Now, Ampere's law, on the other hand, even with the Maxwell's modification, state that a current will create a magnetic field. So now, if the current is changing with time, like in the case of the AC current, that will create a magnetic field that changes with time too. So in other words, in this case, that magnetic field, since it's changing with time, of course, its flux is going to change with time. because the flux is basically the product of the magnetic field with the area. So if the magnetic field is changing with time, its flux will change with time, which means that it will have an EMF. Okay, it's going to generate an EMF. So this could be something that is negative in a circuit. Okay, so when you're doing your wiring, you have to be very careful. Sometimes that may be a problem, and sometimes you take advantage of it. That's exactly what the purpose of this whole chapter is. So what we mean by inductance in this case is that how a circuit will induce effects in a second circuit. So that's exactly what the inductance is. So what we're going to do, actually, I'm going to build this thing in here. Of course, it's not going to work. And I will tell you exactly why it's not going to work. So what I have in here, I have a, basically this is from the kitchen. We ran out of basically paper towel today. I wrapped with the red wire, I think 11 turns, no, 7 turns with the red wire, and 11 turns with the white wire. Wrapped around. So now I have the ends for the wire that is 11 on this side, and the ends for the wire that is red on this end. So what I have in this case created, in a sense, is 2 different wrappings. Now, if I run a current through, doesn't matter, through the white one, for example, and if this current is alternating, it's changing with time. So that current will start from one end, goes around, comes after 11 turns, and comes back from the other end, and now it's changing with time. So it's going to create a magnetic field inside. That magnetic field is changing with time. That means that even if I don't connect anything with this one or connect a resistor, okay, completely resistor by itself, and I don't have a battery in here, so I have this one connected to an alternating current. If that's the case, it has to be alternating, though. It cannot be a battery. So I will not be able to succeed with the battery at all, okay? It cannot be a DC battery, basically, the ones that I have been showing you guys in here. So it has to be an alternating current. So if this current is changing with time, the magnetic field is changing with time, the flux is changing with time. So there will be an EMF in here. The only reason you will have an EMF if this magnetic field changes with time. Then you will have an EMF. Of course, that EMF will also be changing with time, okay? Time dependent. Now you can use this one for whatever purposes in here is. The voltage will depend on the ratio of the number of turns. As I said before, I counted them 11 versus 7. So this will not work for me for the fact that I don't have an AC power source. I cannot plug it to the wall, by the way. It's going to bang. I mean, it's going to make a big noise. So this is, I really need to be very careful with 120 volts on the wall. So I really need an AC source in here to really make this one work. That's one problem. The other problem, when I ran it the other day, even with a 9 volt, I was getting very, very low low currents in it. And low currents translate to very low magnetic field, even if this magnetic field is changing with time, but you're looking at very, very small variations of it. So it's not going to induce much. So this is not going to work for 2 purposes. The fact that I don't have an AC current, at least the one that I can control. And then I also don't have have we been in the lab? We have actually power sources that we can have them change from AC to DC or however we want them. So that is one thing, okay? The other thing also is this device in here, and I actually this is a normal basically power charging device that I have a USB in here. This is actually for my camera that I have. This is not this camera. This is, what is it? Is it upside down? No, it's upside. So this is for a Nikon camera that they have a charger for it. This uses that technology actually, because this plug now connects directly to the wall, which is an AC unit, okay? So now the current will come in here. Let me show you the picture of this, how it's coming. So this is actually what you can read in the back of every device that you have in your household, whether it's your computer, whether it's your TV, whether it's your phone, your watch, which is, I'm kind of sad today because the band on my watch broke. Okay, so I'm not wearing it. Anyway, the point being in here, any device that you have in your household will need something like this. When you look at it, the first thing that you look at is notice in here for the United States. This one takes 120 volt in the United States. That is changing, as you can clearly see, it's an AC current, okay? 60 hertz. But instead of delivering an AC current, first of all, it lowers it down to 5 volt, this one in here, okay? because the camera requires 5 volts. So it's not going to run with 120 volts. They're going to run only with the 5 volts, and this voltage is actually a DC current, not an AC current. Okay, and it gives you up to 0.5, half an amp, basically, a little more than half an amp. That is in the United States, but actually, I was going through this device myself, and it can actually take 240 volts. So this device can actually, you can take it straight out to overseas and start basically charging your phone. The only problem with the overseas thing is at this end, so you really need to have an adapter, which Walmart sells it for like $20 or something like that. Everybody sells it for that. So just an adapter, you plug it to the wall, it's going to charge your camera. Same thing with your computer, by the way. So if you look at the back, that is how you can tell if your device can work outside or not. And again, it takes the 60 hertz of the United States, which corresponds to 120 volts, or takes the 50 hertz outside of the United States, and always will deliver this much power. This basically much, power, which is voltage times current. In this case, that's the power that is going to have from there. Okay, so this is basically what this device is. Obviously, this is written in other languages and other countries and everything else. So this is the device we're looking at. This is the picture that I have of the thing that I actually tried to build in here. But as I said, because this will not work for 2 reasons. For the first reason, I really need an AC current, an alternating current. That's the reason number 1. Reason number 2 is will not work even if I have like a 20 volt AC current, because I know the current that is going to be generated in there is not strong enough to have a decent magnetic field that is going to have a decent flux that is going to induce an EMF in the second part. Okay, does anybody know what this device is called? You have a current in the green wires in here. Okay, imagine this is connected to a power source. Of course, it has to be an AC source. It cannot be a DC source. So this current is changing, fluctuating. And of course, you need at least a resistor in there to tame the current, to control the current. Okay. Otherwise, because the wire you connected like this is going to burn right away, because it has practically 0 resistance. So even if you have a 10 volts in there, 10 divided by 0 is going to have an infinite current. So you have to at least have some 10 ohms in here or something like that to make a current of 1 amp in here running through this. So you have a current in here that is running in this. And the number of turns in here, as you can clearly see, the greens are 1, 2, 3, 4, 5 turns. So I represented them in here by N1. And then you have another wire, a second wire that is coming from this side, and it's turning around. In here you have 1, 2, 3, 4 turns. So N2 in this case is actually 4 from my drawing, okay? But from the one I built in here, N1 turned out to be 11 and N2 turned out to be 7, okay? I didn't do it by design, okay? I didn't mean to have 7 and 11 in here, but that's how it came out to be, okay? As I said before, if the current in here is changing with time, it's going to create a magnetic field in this region, B. Where's my pen? B. And this B also is going to be time dependent, which means that its flux times the area. Here is the area we're talking about. This flux is going to be changing with time. Okay. And this flux changes in all of these loops, basically, in each and every one of these loops, whether the green ones or the blue ones. In particular, the blue ones will have a flux that is changing with time, which means this EMF will depend. And of course, in here, I have to, it's going to have not just one EMF. Each one of them has its own EMF. So I will have an EMF for this turn. I will have an EMF for this turn. I'll have an EMF for this turn. And I have an EMF in here for this turn. So this EMF is going to be N times the rate at which the flux in this one changes with time, where this change in flux is actually in the second part, okay, in this side, in here, okay? And this magnetic field is actually created by this current, okay? So I need to find what this magnetic field is in terms of the first current. Do you guys know what this device, the whole device, is called? That has this region, we call it primary. And this region, we call it a secondary. Does anybody know? Okay. Any guess? At least one person not sure. Has a primary and secondary. Well, that's the question of the day then. This is a transformer. Let me explain what that is. So this is a transformer. Former. There's no R. Okay. So basically it takes, imagine you have a voltage in here. This is called the primary. Voltage in the primary that is generating a current. You need a current in here, okay? And that current would create, of course, its magnetic field. That is the rule, okay? And we know how to find that magnetic field. We can actually calculate it. That magnetic field is just happening in this green wires, which are called the primary in this case. Then the secondary in this case will have its own EMF, okay? So that is actually the secondary in this case, okay? So we have the primary and the secondary, and this whole thing is called the transformer. So hopefully you guys have at least some understanding of how this works in here. So this is the whole topic of this basically chapter. It's trying to find the inductance from the primary to secondary. A key rule for transformer, that is part of the discussion also, it has to have a circuit or a powered by an AC source. Okay, so that is a key for it. If you don't have AC source, the transformer will not work. Does not work, in other words, does not work in a DC circuit. In a DC source, with a DC source, I should say, with a DC source. To go back into my example in here, if you try to reverse the polarity of this transformer, it's not going to work. However, in theory, it will always work if you just take the piece part of it. I tried to actually remove the screw. I don't have the proper screwdriver for this one, but I promise I will try to, because I really don't need it. The camera is kind of an old camera. So if I unscrew this thing in here, remove the cover, if you isolate the DC circuit, if you isolate, the transformer by itself, you can actually make the secondary primary. You can apply the voltage in here, and now your primary becomes your secondary. So always it works backward, okay? In other words, you could have a current running through the primary, the secondary, and that current will create the magnetic field per loop, phi B, and that phi B now is changing enough so that there will be an EMF established in the secondary, which was the primary before. So we will see the difference between the primary and the secondary in this case. So this is basically the topic. That is the main topic of the whole discussion. In addition to the fact now, as I said in the beginning, to begin with, any wire will create, as long as it has an AC current, will have a flux, okay? Especially if it's configured in such a way that it wraps around itself. So anytime that you have a wire that goes in a corner or goes in wrapped around itself, it will have a flux there, okay? As long as, I mean, it will have a flux no matter what, but if that flux changes with time because the current is changing with time, now it's going to impact, among other things, itself. So it doesn't have to have a secondary. Itself, it can be a primary and secondary. So that is called the self-inductance, actually, okay? And self-inductance or inductors actually become important part of any electronic device. So at this point, they become very important. So we're going to talk about the inductance, both of them, the mutual inductance and the self-inductance. Those are the symbols for them. So the first one is mutual, and the second one is a self. Okay, inductance. Mutual inductance is general, and self-inductance is a special case of that. Okay. Of course, we're going to find the energy stored in a magnetic field based on that, because once we introduced the capacitor, if you guys remember, we found that the energy stored in a capacitor, actually by the electric field itself, I'm sorry, the energy stored in the electric field per unit volume, the energy density that was, it was equal to 1/2 of epsilon naught times E squared. Okay. Today, we're going to show that the energy density that is stored in a magnetic field is 1/2 of B squared over mu naught. Okay, so there is a correspondence between the two energies. This energy density is not the energy itself, so it's an energy per volume per cubic meter, joules per cubic meter. Okay, so if you have an electric field, you have energy. If you have a magnetic field, you have energy. So that is what we're going to show. And both of them, in the case of the electromagnetic field signal, you have both of them working together, okay? So that's basically what this thing is. And we're going to talk how to analyze circuits. We're going to do 3 circuits. Most likely this we will not be able to do it today. We're going to do an RL circuit. We're going to do an RC circuit. And we're going to do an RLC circuit. Basically, you have a resistor and inductor. Resistor and capacitor, inductor and capacitor. Okay. And then, so we're going to do an RL, an LC, and RLC, okay, together. So this is the most general circuit that we're going to have in this class, which is the RLC circuit, which is really the most advanced circuit. We're going to take the easy case of all of these devices in series. And if you're going to take electronics or electrical engineer or something like that, you're going to do far more complicated circuits than this, okay? We're going to take a simple case. We're going to talk about resonance, and we're going to basically talk about the, I don't know if we should do that or not, basically for the how to filter certain frequencies, okay, using this kind of circuits, okay? And then that's basically the part at the end, and we're going to talk about did you guys do resonance when you did the physics 4A? You guys remember that or not? Physics 4A? Yes, no? Okay, so it's going to be very, very similar. As a matter of fact, we're going to draw an analogy between the mechanical system between physical 4A and this case. So we're going to do an analog. These are called analog, by the way, circuits, okay, as opposed to digital circuits where you include actually diodes and also transistors. And there will be correspondence 1-to-1 between an electrical circuit, namely between the inductor and the mass. The inductor will play the role of the mass, the inertia, exactly. That's what it's going to do. The resistor will play the role of your old friction, okay, the force of friction. And the coefficient of force of friction, I guess you guys used the letter B for it when you were doing physics 4A, unless you use different letter, which is fine. And then also for the capacitor, or 1 over the capacitor to be more specific, will play the role of the constant K for the spring. So this is a mechanical system, and this is an electrical system, analog electrical system that is analog, okay? And this presents a big advantage because instead, for example, of simulating how big a building, for example, is going to work, and you have a mechanical system with a building with its own basically inertia, with its own friction, with its own basically leeway for the oscillations. So you have its spring constants in there. So instead of doing that, and it has so many of them, probably coupled system, you have not just one, but you have so many of them attached to one another. So instead of doing that, what you do, you go and make a circuit similar to it using these components, inductor, capacitor, and resistor, in such a way that the mathematics would look the same. So, and then you send the signal. You send, for example, a power source to it and see how is the the circuit will respond. Based on that response, you will see how the building will respond. So in this case, you have simulated a mechanical system using an electrical system, and instead of really wasting a lot of money in building the actual building and then find out that that's, for example, you needed a larger K or a smaller K or a larger B or a smaller B, or you needed to reduce the mass or increase the mass or do something in the joints where, for example, the coupling needs to be different, then in this case, you have saved yourself a lot of money by just finding that information from your analog system, the equivalent to it, okay? So this is the equivalence between the two, okay? So this is what we're going to draw at the end. And this is actually the case in here, that there is an analogy between the two. And instead of having to go and waste, you can really simulate your mechanical system using what you know about electricity, okay? Because the math will turn out to be identical to what you guys did in physics 4A. Okay, I know that in physics 4A, you have the equation m times the acceleration. I'm going to use the one-dimensional time, plus the coefficient of friction, which was the letter b, times the velocity divided by time, plus, of course, the spring constant k times x is equal to the force that causes the whole oscillations, which is sometimes time dependent. This is for one mass in the spring and attached to a viscous system where the coefficient of viscosity was b. In this case, we're going to have this similar equation at the end, L times the rate at which the current will change with respect, I'm sorry, the charge with respect to time, plus in this case R times the current, which is Ohm's law, by the way, and the current is dq over dt, plus 1 over C times Q, that is the difference in potential inside the capacitor, is equal to the power source in this case, which is time dependent, okay? This is the EMF, but the EMF may be time dependent. The math is identical, except instead of K, you have 1 over C, instead of R, you have B, instead of the mass, you have L. So that's taking advantage of that analogy. Solving a mathematical system for a mathematician doesn't care which symbol you use, whether X or Q, so to go back further into my analogy in here, X represents in this case, X in this case, the position represented by the charge Q, okay? And the velocity is represented by the current, okay? So you have all of the parameters that are identical from a mechanical system to another system. So this is chapter 30, which is a beautiful chapter, okay? So let's go back into this situation in here, and let's find out exactly what we need. Before I do that, and I don't remember, I think I kind of big on it right now, we did define using Ampere's law. I think we use a different technique to find the magnetic field due to a wire, which we did actually the integral, okay? So we found the Ampere's law. I think we did also Ampere's law using that. So the Ampere's law, so if we're going to a distance r from it, okay, the circulation for the magnetic field in this case over this radius is going just the circumference, 2 pi r, times the magnetic field, and this is equal to the current enclosed in here times mu naught. So this is basically what Ampere's law was saying. Okay, that's what we did. We're going to take the solenoid, which I don't remember having done that, honestly. So we're going to take a solenoid, which is this device itself that I was talking about earlier, but we're going to wrap just a number of turns on it. So we're going to take a number of turns in here, 1, 2, 3, 4. So just a number of turns, but I'm going to assume that I have actually n, where n is the number of turns per unit length. I don't want to take 4 of them. I want to have a huge number, okay, per unit length. In other words, if I consider L length, I have NL, okay? This is an L length, okay? So the unit for this one is per meter. So this is the density, how packed the wires are. Because in the practicality, let me show you how this thing is. It can be pretty involved. See, there's so many wires in here, okay? So many tiny wires like this one running around. So instead of counting them, they give you the number per unit length, okay? So which is a number per meter. You have 300 wires 300 turns per meter, or 200 turns per meter, or 17 turns per meter. So basically 17 turns, they are very much spaced, okay? So that is basically what this number is. It tells me how many turns they are. So I'm going to apply Ampere's law to find the magnetic field inside. Okay, because we will need this B for our calculation. Remember what I said to here, we need that B here. If we don't have that B, we're not in business. So we really need to find the magnetic field inside. So I'm going to make a mathematical cut. So here is how this looks like. So I'm going to cut it right in here. But of course, if I cut the wires, this thing is not going to work. But it's just a hypothetical cut. So this is how this whole thing look like. So I have my device now cut mathematically into two halves. So basically, this is the, I'm sorry. So I have the wires going in and coming out, going in and coming out. Of course, the cut is made there, and so on and so forth, okay? And so on and so forth. So this is another way of looking at it. The wires where the current comes from there is going to be represented by current coming out of the screen. Obviously, this is a very, very long device, and we call it solenoid. Okay, and in here, the current is going in. So this wire is extended for a long period of time before I see the end of this one, okay? So it has a very long area in here. It's coming out from one side and going in. So this is not a real cut. If you cut it, there will be no current. If you actually go and cut it with the whatever device you want to cut it with, there will be no current. So this is just to visualize it, to see where it is. So we're going to make a mathematical cut. I'm taking an L region of this wire. I know I have N times L turns, because N is the density of the wrapping. How many turns do I have per unit length? But I took L length of this, so I know I have NL turns, okay? This is the number of turns. So in other words, how many currents coming out in here? N times L. L is not a part of the problem, as L is not real part of the problem. So I know I have a solenoid that is extending very, very long, infinite solenoid, basically. I want to find the magnetic field outside, and I want to find the magnetic field inside, okay? The magnetic field outside, I'm going to use an Amperian loop that looks like this, okay? And I'm going to go on it counterclockwise, just to make sure my mathematics works correctly. Well, if that's the case, how many currents I am enclosing here? There is no current inside. And if I calculate the circulation, let me, for the sake of argument in here, the length, again, the width is W and the length is L, okay? I'm going to argue that the magnetic field must be, of course, perpendicular to the current, okay? But this outside in here doesn't matter, because outside is going to be zero anyway. 0 times mu naught equals to the circulation of the magnetic field over this entire path. Since that is, there is no magnetic field in there, there is no current in there, so there should not be times the circulation. There should not be any magnetic field outside completely. The reason being is the following. First of all, I really need to make the case for argument for symmetry. The magnetic field has to be perpendicular to the electric field. So it cannot, it's either this one or that one. But if you say it's one of these two, then we have a problem, because the issue with it is the, if again, I spin it, move it up and down, there will be different magnitudes in here for the magnetic field. The point being in here is that there is no current, so there should be B is 0. And this is, of course, if you say, for example, at infinity, the magnetic field will be 0. That means I have to take this W very, very long. Since it's 0 from one side, it has to be 0 from the other side. The bottom line is B is 0 outside. Same thing in here, B is 0 outside, okay? I can use the argument with the influence of the loop at infinity, since there is no magnetic field, no currents at infinity, there should not be any magnetic field at infinity. Therefore, the magnetic field at infinity is 0. So I could make W infinite and may argue that the magnetic field on one side is 0. Therefore, it must be 0 also here, because the sum of these two quantities are 0. Okay. So that is basically the argument that I'm going to make in here. So the magnetic field is 0 outside. This is similar to the capacitor, where we argued that the capacitor, the electric field outside is 0, but the inside is not 0. This is the same thing. This device, as long as it's a long one, is going to trap the magnetic field inside between its plates. So B is not equal to 0 inside, and B is 0 outside. So let's take now an Amperian loop that is like this. Again, I just argued that B in this situation cannot be 0 on this side. B is some value in here. And since the current is coming out, according to the direction that I have in here, B is going to be pointing down. Think about it. If the current is coming down, it's coming out, okay? This is going to circulate in this fashion. Since it's circulating in this fashion, B must be going down. And the circulation, since I chose it to be clockwise, it's also going down. So B times this length is going to be just, where the length is L actually, is just B times L. Because remember, this is a dot product. This is not the straight out product. So B times L, since both of them are parallel, is just going to be B times L inside. Okay. Outside is going to be 0, and here it's going to be 0 because there is no magnetic field outside. And here it's going to be 0 because the circulation is happening in this direction. And the magnetic field, I just argued, it has to be pointing in here. So there is a 0 because it's cosine of 0. Again, this is a dot product. Since the magnetic field and W are perpendicular to one another, the cosine of 0, cosine of 90 degrees is 0. Same thing in here. We're circulating in this way, and the magnetic field is pointing down. So the angle in this direction is actually this negative angle, which is a negative 90 degrees. But then it's actually pointing this way. Then in this situation, or this whole thing, one of them is negative anyway, when the other one is positive, it doesn't matter. Cosine of 90 degrees or cosine of negative 90 degrees is 0. So the only thing that is going to remain is B times L in this region. So the circulation of one side is B times L is equal to mu naught times the current. And the current, I have so many of them. I don't have just one. I have so many. I have N times L turns. That means N times L coming out times each one of them is carrying a current I. Okay. So it's going to be N times L. That is the number of turns that's coming out per unit length. But I took an L length for the Amperian loop, and then times the current. I cancel the L from both sides, and I find the magnetic field inside the solenoid. It doesn't depend on L because L is a fictitious. It's just a made-up thing. Okay, it's an Amperian loop. Okay, it's a loop needed for Ampere's law to work. It's just like a Gaussian surface. This is also a made-up thing. So the property that I included for it, which was the length, the length L, has to not the answer should not depend on it because it's really a fictitious loop. It's not real. The whole cut is actually theoretical. The whole cut is fictitious, is not real, because if we do it, there will be no current. This whole thing will give me 0 magnetic field. So it's going to be mu naught times the num n, which is the number of wrappings, times I. So this result is worth remembering. So this is the magnetic field. Magnetic field inside a solenoid. I should make a point of the fact that this is a long solenoid, okay? Similar to when we did the capacitor, we said the capacitor is supposed to be an infinite, basically plane, but we used that property and we found the answer. And we said that there are edge effects when you come close from the edge of the capacitor, and we use that formula all the time for the capacitance. Same thing in here. We're going to take an infinite solenoid, and we said, what I am arguing also, if you come to the edges also, this formula will not work, okay? But inside the solenoid, this is perfect. This would give me the magnetic field. This result is worth remembering. There is another kind of solenoid, which is actually a toroid, which is this shape, basically. You take the turns now and you wrap them on a donut, basically. So this is basically what you have. So again, you take the currents from one side coming out, from the other side going in. Doesn't matter which one you take, okay? So let's take this one going in. And the same turns now, because you have a difference in radii. Basically, what you have, you take the wires and you start wrapping them around a solenoid. You find a lot of this solenoid exists in circuits. A lot of them are actually of this shape, okay? But it's the same number of turns now. It's not, they're not different, okay? So I have a fixed number of turns, n turns now. So this is not infinite. This is just a solenoid that has this shape, and you wrap the wires, and at some point the wires will come out from the other side. So basically, let me make it look like, so let me take a different color to explain how this is working. So you take a wire, it comes in, and you wrap it, and you wrap it, and you wrap it around the donut, basically. It's the same wire, okay? But it's wrapped so many times, depending on how packedly it's right. And then it's going to come out here, okay? So this is what I'm showing in here. So the current will come in here, will go around, same current, and come out from the other side. Similar to this turning in here, because the way that we started with was this one. And when we made the cut, it looks like that one. Same thing, we're gonna take the cut in here and look at this current. So this is how it looks like now. So when you cut the donut right in the middle, okay, in order to put the cheese in it, okay? Not the cheese. The other one is the one you do to cheese. Bagel, okay? So this is where the current is coming out, and basically it's wrapping around, okay? So it's come out and then goes in, comes out and goes in, comes out and goes in. So I'm trying to find the magnetic field inside this region in here of radius r from the center, r. So if I do that, then the circulation of the magnetic field, again, I'm going to circulate it on one way or the other because I know which way the currents are. Either the magnetic field is going to be pointing in this direction or in the other direction. Since the magnetic field is going in to the picture, so it's going to circulate, in this case, counterclockwise. So it's going to go like this. So the magnetic field is going to be like this, okay, going inside. So I'm going to circulate it also counterclockwise because I don't want to deal with the sign. I know which way the magnetic field is going to point. So the other side, I'm going to just write it positive because I want to circulate also in the negative direction. So B times the circulation is going to just B times 2 pi r, because the circumference of the circle is 2 pi r, is equal to, again, I took n turns now. It's going to be mu naught times n. This is not the packing. This is the actual number of turns times the current that is running through it. So the magnetic field inside the toroid, this is the shape that is called toroidal solenoid. Okay, that's this shape. It's not a long wire like the first one, okay? It's not a cylindrical solenoid. So the first one was actually cylindrical solenoid, just to make the distinction between them. I mean, this is used also, but mainly the one that is you find in your circuits is the second one. So in this case, it's going to work to give me B is equal to mu naught times n turns times I divided by 2 pi r. There is an interesting result in here, and that is, what if r becomes so big? So this result also is important that we will need, okay, for our homework, for our problems. So this is the magnetic field inside that region. It depends on r. The first one was independent of anything, just the number of packing, that's it. And the current, of course. And mu naught is just, if you change mu naught and put a different metal, and you find that a lot too, use a metal in there, it's going to improve the magnetic field because it will have a, not mu naught, but it's going to have a km times mu naught, and km is more than 1. So in a different material, when you include a permeable material inside of it, this expression will be just K, the magnetic field of K, the relative magnetic field, depending on what metal you put in there, improved over this expression times Ni, where K now is just the new mu. Mu is equal to Km for the material times mu naught. So this is the relative permeability that depends on the properties of the material. So again, this is similar to what we did with the capacitors when you put a different material in there with different dielectric properties. So instead of having epsilon naught, now you will have actually epsilon K times epsilon naught. Just to make the distinction between the two, in electrical circuits, I mean, in the case of the electric field, you have the permittivity, which is K times epsilon naught. This one is Km, just to make a distinction. This is actually the magnetic permeability versus the electric versus the dielectric, basically, permittivity. So there are two different things in here, just to make the distinction between them. We add the M to one of them. Anyway, this is basically for this cylindrical solenoid. But for the toroidal solenoid, the expression is this one, and it's interesting to see, can we recover one from the other? In other words, can we make this donut or this bagel so big so that its radius becomes infinity? If it's, of course, infinite, that means you're back to, for a small region, it looks just like a cylindrical shape. Imagine the entire galaxy. You wrap a wire around it. Of course, if you're sitting inside of the place where you are, you don't see the entire galaxy that it is actually has this donut shape. As a matter of fact, the Earth itself is circular. It's actually a spherical shape. And if you look outside, it doesn't look circular. It looks flat to me. So it looks like a solenoid, at least on a certain regions. It looks like it's cylindrical, at least you're sitting on a flat surface at some point. So if R goes to infinity, N over R, and if R goes to infinity, then the ratio, of course, the number of turns will increase to keep the same number of packing. So N also needs to go with it. So how many turns you make will depend on that too. So N also goes to infinity. If you keep the ratio of N over 2 pi R constant, this becomes your packing. How tightly you wrap the circuit around the galaxy or anything that is huge. Of course, you don't need the galaxy, as long as it's 2 meters probably long versus, for example, 2 centimeters, that becomes a huge number. So you don't have to go through the entire galaxy. The expression will be the same. That is my point. Because this N over 2 pi R is exactly what we had before. So the two match, the two types of solenoids match, okay? So we need this expression. Now, we go back to our problem in here, unless you guys have a question about this one. So what is it? We had a one solenoid, basically, where we wrap the turns around it. So we know what B is. We know what the area is. This is the area. It's an engineering thing, okay? So we can find the flux of the magnetic field. And then from there, we're going to find the induced electric, basically the EMF on the other side, okay? So let me continue down. I'm going to define M, the mutual inductance. By definition, the book was kind of vague on a little bit because I looked at the book. This is one of the issues that is kind of, I always look at. So the number of turns in the secondary, N2, in the secondary, times the flux in the secondary, per turn, for each turn, not per turn, for each turn. The reason why you need that, because then it gives you a leeway to add as many turns as you want. So if you did not do 11, you could do 12, you could do 14, whatever number you have. So that's why you include the number in the first one, is by definition how this is deriving from the current in the primary. So the primary has to have a current in it to change the flux in the secondary. So we call this mutual inductance the effects of the primary on the secondary. So this is the mutual inductance, or how the primary induces a flux, changing flux in the second. It doesn't have to be changing. This is a flux period. Even if it doesn't change with time, if I1 is fixed, there will be a flux in the secondary. Would you have an EMF? If only and only if I1 changes with time. So this is by definition the secondary. Now I could do the same thing. I could replace the primary, make it secondary, and the secondary make it primary. So then I would define the following. The number of turns in the primary then, because it's going to be the secondary, is going to be related to the same quantity. How is the flux changing in each turn? Okay, or how the flux on each turn, I should say, doesn't have to be changing yet, is how is the secondary is inducing, basically affecting the primary by running a current in the secondary now. Okay, there is a theorem in calculus. What is the book? Here. This is the only book, and I've been looking for this one for a long time, okay, where there is actually a proof for a mathematical proof, of course, not a, because when you take this class, and the book was kind of vague on it, M12 is equal to M21. In other words, the two basically mutual inductances are the same numerically, and the proof is actually on page 313 of this book. Okay, so I bookmarked it in here. And the definition is actually related to the fact that you took that in outside. So the only thing that relates then is the geometries between the two shapes, okay? Between the two. So if this one is basically overlapping with the other one through this, just basically this part of the area, that's basically why at the end, the mutual inductance turn out to be the same. I mean, I would encourage you to look at it if you have time, especially if you're going to go into the mathematical physics part of it, where it's actually the integral there is interesting to show that the two are the same, okay? The book was vague on why N2 and N1 in here are needed, and they are needed because of how the mutual inductance is actually defined, okay? It's not a choice for why N2 and N1 are taken out. Then in this case, the mutual inductance is the same. So in this case, I'm going to represent it by the letter M, period, end of the story. Okay. So let's summarize this thing in here. So you have a current in the primary. Current in the primary. That current in the primary will create a magnetic field. We just saw the value for the magnetic field. Here is a magnetic field that it creates, where I1 in here, where I is represented by I1, okay? Now, that magnetic field B, so if you wish, in this case, B was simply equal to mu naught times the N1, the density, how packed they are, okay, times I1, okay? That is a magnetic field. Now it's across an area A. Then in this case, I can find basically the flux. That flux then, if I multiply it by the number of the secondary, N2 now, okay, then in this case, I have found the mutual inductance. So in other words, I can find what this M is. Okay, so what this M is. So N2 times the flux of the magnetic field, which is the area, times the magnetic field in that region. And the magnetic field is just across one of them. So it's going to be B, which is equal to mu naught times N1, because this is created by the N1, by the way, okay, times I1, okay, is equal by definition to M times I1. Cancel the I1. And from here, I have the mutual inductance, which is N2 times A times mu naught times N1. N1 is actually N1 divided by how high how long is the solenoid. This is identical to the result we found a long time ago for the plates, where it depends. We said it's an infinite plate, but at the end we were forced to find its length, okay? To find its area in that case, okay? Divided by the distance between them. So it has to do with that. So this is the mutual inductance in this case, okay? This is not as important, if you wish, as the self-inductance itself, okay? If you're curious trying to find the EMF in the secondary, which is important, by Faraday's law, the EMF in the secondary is just the rate at which the flux is changing with time. The entire flux changing in time. Well, the entire flux in this case is just n times the individual fluxes. So E2 is equal to minus the change at which N2 in the secondary is changing with time. Obviously, N2 is independent of time. So N2 times the rate at which the flux in individual turns is changing with time. And the flux of individual in turn changing with time is just given by this expression where I1 is actually the time dependent in that turn. So in other words, you have an EMF in the secondary now. And this is the EMF for it, where the flux phi B is given by the area A times the magnetic field, and the magnetic field is equal to mu naught times N1 times I1, okay? Take the derivative with respect to time, and you'll end up with dit over dt. So in other words, I can actually write it in terms of the mutual inductance now. And the fact that this expression itself is equal to m times I1. So this expression then becomes with N2 in it. So epsilon 2 becomes minus M1, minus M in general, times the change of I1 with respect to time. All I did was N2 phi B, by definition of the mutual inductance, is just M. This is from the book page. It's M times I1 from this expression, okay? Where this is the M, the same thing. So in this case, the mutual inductance, the secondary voltage based on the primary, basically current, okay? This is the mutual inductance. How are we doing on time? Still have a little bit of time. I'm going to define the self-inductance in the same fashion. So the self-inductance now, there is no need for 1 and 2, no indices, okay? Because it's the same wire, basically wrapped around itself. So if you have a current I in it, it's going to have an inductance self-generated 1. In other words, it's going not to like the change in the current in itself. So it's going to have, by definition, an EMF in this case that opposes the change in the current. And this EMF by definition is minus L di over dt, where L in this case is the self-inductance. From now on, we're going to drop this mutual and self, and we call just L the inductance, period. Okay, both L and M, the same thing, have the same dimensions, because both of them are voltages divided by the rate at which the current is changing with time. Both of them have the same units of volts divided by amperes per second, or volts times a second divided by an ampere. And remember, the volt has the units of a joule divided by a coulomb, and you can find the definition in terms of SI. We call this one an H for Henry. So this is the unit for an inductance. The unit for the inductance is the Henry, okay? Let's go back into that solenoid, one of the two, doesn't matter which, okay? We're gonna go back and calculate the self-inductance for this wires, okay? So imagine with me that I wrapped only a single wire on itself and basically trying to see how much is the EMF in this case. Well, I can find the magnetic field in this case, in this situation. And the magnetic field is given by B equal to mu naught Ni. We just found out that, okay? And then also I can find the, if I assume that there is a cross section in here, A, then the flux due to the magnetic field is given by A times B. And A times B is just mu naught N I times the area A. Let me write the I at the end. Usually that's how we do it, okay? So this is the flux in the magnetic field. Now, if I multiply the number of turns times the flux, this must be equal to the inductance. So L in this case is equal to N times this ratio of B, phi B over I. So it's N times mu naught N times A. There is a distinction between N and N. This one is equal to N over the length of the solenoid. How long is a solenoid? So in other words, to be more careful in here, this is equal to mu naught times N squared over L times A, or alternatively, it's mu naught times N squared times L times A, okay? Whichever you like, doesn't matter. So if you give you a number of turns, and they tell you the length of the solenoid, and they tell you the cross section, then you know it's inductance in Henry. Similar to the geometry, when they give you the area for the capacitor, A, and they give you the distance between them, D, then you know the capacitance in this case, how much it is, epsilon naught, 1 over epsilon naught, epsilon naught times the quantities that you have in there, A times L divided by L, okay? Times D, divided by D, I'm sorry, okay? And that was in farads. This one is gonna be in Henry. So this depends on the geometry, that's all. Because L is the length, A is the area, N also is the engineering, how you pack this, how hard do you want to pack them, and this depends on the medium. Usually, like I said, you put a permeable material in there to increase the permeability, to increase the inductance in this case. Same thing like for the other one, we increase the capacitance by putting a dielectric material between the plates. That prevents it also from collapsing on itself, becoming a conductor, okay? Not charging at all. So the same thing in here, okay? So this mu naught, think of it as mu in general. So it's mu, which is Km times mu naught. So if you put material in there, and that's what you do actually most of the times, okay? So this is the inductance, and this is basically depends on the geometry, also on the packing, which is the engineering, and on the material between or inside the solenoid. I know I did a long solenoid, okay? I did this long one, but it's the same concept even when we do it for the second one. It's the same idea, because in that case, it's this area in here. This is the area that we are concerned about. Okay, so this is the area in this situation. Okay, that we want to see how much you have in there. Okay, and where you wrap the first one and where you wrap the second one for the mutual, or you wrap the single one for itself for the self-inductance, you're going to have the same definition in here, where in this case, B times this area now, okay? If I take the current in this direction, B times this area is going to be the flux. So B times A, and it just found B from the previous calculation to be mu naught times the number of turns N divided by 2 pi R times the current running through it times the area A. So this is B times A, which is phi B. Okay. If I want to find now the self-inductance, not the mutual inductance, in other words, N is the same. So in this case, the self-inductance L is going to be remove the I from it and multiplied by the number of turns. So it's going to be mu naught n squared divided by 2 pi r times the geometry A, times the area A. R also is important now, okay? R is this distance. In other words, the radius of this thing in here. So this is the similar expression, but this inductance now depends on the radius. It depends on how the material is basically compacted. Okay, we still have another concept, and I'm going to basically close on it, which is the idea of the energy, okay? I just argued that the EMF in this capacitor, in this inductor, I'm sorry, is given by this expression, L di over dt. This is the EMF, okay, generated in a self-inductor. In an inductor from now on, we're not going to call it self, okay? We drop the letter self, okay? Now, if I'm interested in how much energy it takes to build a current, how much energy to build a current. So in this case, what I do in this situation is basically we multiply dq, because we already have a voltage there in the capacitor. I'm going to take it in absolute value because I don't care about the sign right now. The sign, all it does is opposes. It doesn't like to be done. Just like the mass, when you try to push it, it doesn't like to be pushed. It's going to oppose. So you build the kinetic energy with a certain velocity. Same thing in here. You're going to build an energy in this case, an inductance energy, an electrical energy in here, once you have the current running. So that's what I want to find. So in this case, it has already an EMF in it. So the next needed energy to overcome that, that's where the minus is coming, overcome, okay? So the energy needed, du, so this is the energy needed to add dq charge, okay? Is going to be dq times the EMF, in absolute value, of course, because I already found the signs in here. So it's going to be L times di over dt times the next dq. I'm going to shuffle this expression a little bit and write dq over dt is actually I. So this expression then for the energy needed, du, is going to be, this is the big U, okay, is going to be L di. I left with di in this expression when I moved the dt to the other side, times dq over dt, which is I itself. So this expression then, for the energy going from zero current all the way to a finite current, is going to be just the sum from 0 to I of this small increments of energy, L di over dt. Take the L out, and basically you will be left for the integral from 0 to I of I di, okay? And then the energy then, the integral of x dx is just 1/2 of x squared. So it's going to be 1/2 of Li squared. I'm sorry, Li squared. I already put the upper limit. So if you have a current running in a solenoid, you already have an energy. And this is the energy in joules, okay, in a solenoid. So this is how much energy you have when you have a certain current in it. As long as you know what the inductance is, as long as you know what L is, or not, you can go and calculate it like I showed you earlier. So now you have an amount of energy in joules. So I'm going to go back to this expression. Of course, we will need this expression big time when we're doing calculations. So this is expression that is very important that we're going to need. So what I'm going to go do now, I'm going to go back to the same solenoid, the long solenoid. And again, the argument can hold the same thing. I think the book did it for the donut-shaped solenoid. So we're going to do the long solenoid just to make a distinction between the two. Okay. So the long solenoid is actually easier. The long solenoid. So I'm going to assume that there is a cross-section A. I know what L is for this one. I just calculated it. It's somewhere in here. L for a long solenoid is N times mu naught times N times A, or N squared over L times A, whichever expression you like, okay? So this is how much energy then is stored in it. L, as long as I have current. Of course, I have wires in here. Otherwise, this thing will not work. Okay. So L is equal to, according to that expression, pick and choose. N squared times A times mu naught divided by L, divided by, little l. Little l is the length, okay, just to make the distinction, because in this, everywhere, in all of the notes, they use big L, okay, for the inductance. So that's why I'm using little l to make the distinction. So it's mu naught times N squared over little l. L is the length in here of the solenoid. An actual length, not an Amperian length. This is an actual. Okay. We're not doing ampere anymore. We did just to find what the magnetic field is. Times, of course, the area. What is the expression? Times the area, and the area again is this area itself. Okay. So this is L. So if I have a current running through it, this is how much energy I have. And energy is equal to 1/2, of course, that's from that expression, times L, and L is mu naught times N squared over L times A. Okay. Alternatively, I can multiply it by L, and I am having in here the energy is equal to 1/2 of mu naught times now N squared divided by, I multiply by L, now I have N squared times LA. Remember, N over L is equal to little n. This is the packing the density in here, okay? Of course, times the current squared. This expression times the current squared, I squared. Don't forget that you have to have a current in here. Here is the expression. So this is times I squared. Well, I just also found the magnetic field in this region. The magnetic field, if you guys remember, B is equal to mu naught times N times I. We just found it earlier in here using Ampere's law. Somewhere in here, okay? Mu naught N times I. Having that expression, I can replace the value of I squared using this expression. So the value of I squared is equal to B squared over mu naught squared times N squared. So I'm going to replace it back into the expression for the energy, and we're done. So the energy U then is equal to 1/2 mu naught N squared LA times B squared over mu naught squared N squared. Cancel the N squared with the N squared. Cancel the mu naught squared with one of the mu naughts. And the B squared stays in itself. And the energy then is going to be 1/2 times B squared over mu naught, that is left in here, times L times A. Well, L times A is just the volume of this thing. This is A. This is L, the length of the solenoid. So this is L times A is just the volume. I'm going to define the energy density as just the energy per unit volume. So the energy density for the magnetic field is defined by U divided by the volume itself. And that gives me the other expression that I needed today, 1 over mu naught. This is as opposed to an expression that we found. This is a very, very important expression for us. Okay. As opposed to the expression that we found a long time ago when we were doing the electrical signal, we found it to be the energy density also. This is joule per cubic meter, not joules per, not joules, period. This is energy density. Because I divided by the volume to find it. So the energy U also was equal to epsilon naught times E squared for the electrical current. This is in addition to this expression, because soon we're going to solve Maxwell's equations and we will need the both of these expressions. So today's discussion point, hopefully you caught the first one. Okay, you caught it, I should say. And that's the only one today, because I know you guys have an exam to do. Okay, I think we still have about 6 minutes before the class is over. But just to summarize what we just did today, we talked about this effect a lot. We talked about the induced EMF and how to calculate the energy stored. Okay, we still have a big chunk of the chapter which is in here. Okay, which will run actually to chapter 31, because that's also an AC current. Okay. I know you guys are thinking more about the exam than anything else. And Christopher, do you have a question?
Yes, I do. I think something else went wrong with the exam 3 because it says that it's also due at 2:30.
Are you serious? Okay, thank you for. Okay, let me go and fix that then. Man, where is the assignments? Due 2:30. Man, that's horrible. You're right. How is it now?
1 sec, let me check. Due at 8:30.
Okay, very good. Thank you.
No problem.
Okay. Okay, guys. I will see you, I think, a week from today because Wednesday we don't have a class. Please send any messages if you see something is wrong with the way setups, the exams are set up, because a lot of these things are online and sometimes you have so many things thinking about and you forget to, and you miss something or the other. So I'm going to stop the recording.